Welcome. So the plan for today is we will continue working with non-homogeneous second order differential equations. So last class and on the reading quiz, we practiced how we can think about coming up with guesses for what a solution might look like for non-homogeneous systems. And in particular, how do we recognize resonance and what do we do to account for resonance in those situations? So just to kind of catch up, a summary of last time. Again, we were talking about solving these sorts of functions, differential equations, excuse me, where now we no longer have zero on this side. So I'm just going to call this the forcing function. And so the process for finding a particular solution for these differential equations was to kind of say, well, we're going to guess a solution that has the same form as the forcing function. So if our forcing function is a power function, then we're going to guess a polynomial that has the same degree. If we have a cosine or a sine, then we talked about why we need to include both of these. And let me correct that. Right, we would want to include both the cosine and the sine terms in the guess. And if we had exponent as the forcing function, then we would guess an exponential function with the same power. But we did need to be careful to see if our guess has resonance with the homogeneous solution, then we might need to multiply by a factor of t in order to correct for that. So once you come up with your guess, take into account whether there's resonance. Then you plug your guess into the differential equation and solve for whatever undetermined coefficients you might have. So we were mostly just focusing on coming up with the guess and not too much the algebra for how we solve for those coefficients yet. But any questions about this process or anything that came up on the reading quiz?
Did have a question about the quiz.
Yeah.
Two of the questions seem to be almost identical, and yet they have different answers.
Well, the forcing functions were all different, right? So the a, y prime, b, the left side of the equation was the same. The right sides were all different. So it's really the right side of the equation that determines what the guess is going to be. So if you have different right sides, you're going to have different guesses. And that's why you would have different answers for each of those. Anything else? And so just kind of some general things while I'm thinking of it. We were getting messages from Zoom telling us that we need to either put a password on our classrooms or put a waiting room, which means you wouldn't be able to get into the room until I approve you, which is super annoying because while I'm teaching, I have to sit here and approve waiting rooms. And then we were just told, you can confirm this if you've heard similar information, that is no longer the case. So we've been getting emails that this is going to be in effect on Monday. And now I've been told that is not the case. So I'm not going to put a password on this room. And let's just hope everything works smoothly on Monday. But you might just want to try and come a couple minutes early just to make sure that it's working okay. And one other thing I just want to share. So thanks everybody for your responses on that survey. We have 80% response rate. So that means you guys have your 2 points for the exam. So far so good. You've all got 2 out of 100 on the exam. And so here were just some of the feedback that I received from the class as far as, difficulty and whatnot. So as far as the pace, seems like things are going generally okay. A few people thought it's going a little too fast. And as far as what students were doing for the reading quiz, in case you're curious what your classmates are doing, it seems like the videos are helpful. And that was all I really wanted to know because they take time to make. So I just wanted to make sure they were actually useful, or else I would put my time into other things. But seems like that is useful, so I'll keep on going with that. And as far as the difficulty goes, I think this is probably pretty normal for a class. So I think things are going okay so far, generally speaking. But if you find that you're having some trouble, please reach out to me, and I'm happy to help. It might not be that you need to put more time into the class. It just might be to manage that time differently might make a difference. Okay. So unless there are any questions, let's continue then finishing up this worksheet 11 that we were working on last time. So we got through basically questions 6 and 7, where we were identifying whether a differential equation had resonance or not. So questions 8, 9, and 10, these are just asking us to come up with what a good guess would be, not necessarily find all of the values of the coefficients. So if we're working on question number 8, then right, the first thing to do, because we're going to need to identify whether or not we have resonance, is to find the homogeneous solution, which in this case would be the solution to y double prime minus 6y prime plus 9y is equal to 0. So again, this is just to help us identify whether or not we're going to have resonance in our guess. And so here I'll kind of bypass this, but you can see that the characteristic equation would have 1 double root of 3 in this case. So our homogeneous solution, when we have a repeated root, would look like e to the 3t plus c2, oops. Right, so that would be our homogeneous solution. And because it's a repeated root, that's why we have this extra t over here. Any questions about that? Okay, and then we look at our forcing function, which is, in this case, 5e to the 3t. And we want to come up with a guess for this based on that. So I'm going to use subscript of h to denote homogeneous solution. I'll just say the reading materials use a c here instead of an h. So they use a subscript of c for homogeneous, which seems weird. The subscript of h seems more descriptive for homogeneous. And they do use the subscript p for a particular solution. So if I'm working with this one, again, we kind of look at this and we would say, okay, seems like I'm going to guess a function that looks pretty similar to that as my guess. And does this guess have resonance with the homogeneous solution or not? Okay, we've got a vote in for yes, there's resonance. And there is here because what we can see is this is basically exactly the same as that, right? So if I were to try and take this particular solution and plug it into the differential equation, I know I'm not going to get this, I'm going to get 0 because this is a homogeneous solution. So that's not going to work. So we said we can multiply this by t. And we're not done dealing with the resonance at this point, right? We have this term over here, which is the same as this term over here. So we still have resonance when we multiply by t. So what do you think would make sense to try and do here? To try and fix this. And the problem is, if I plug this in to the differential equation, I'm going to get 0. There's no way I'm going to get 5e to the 3t because this is a homogeneous solution. So what did we do to take this homogeneous solution and say this might be a better guess?
Could you multiply it by another t to make a t squared term?
Yep, that's right. So we just keep multiplying by powers of t until we get something which is not a homogeneous solution. So in this case, our guess would have to multiply another power of t. And now we can see that this is not the same as either of these terms here because this has an extra power of t. And that would be a good guess to go with that you can then plug into the differential equation and try and solve for a so that you get a 5 in front of the e to the 3t. So any questions about how we are identifying resonance? I think that is the trickiest part here. So I'll just say there's kind of two ways to think about resonance. And if you don't have any questions, then maybe this way is working just fine. But yeah, so one way to do it is to take a look at your guesses and see if they look like one of the homogeneous solutions. The other way to think about it would be to say, okay, what would be the corresponding root of the characteristic equation if we had an e to the 3t in our solution? And you can then say r equals 3. Then we can say if when we find the homogeneous solution, if r equals 3 is a root, then we're going to have resonance. So that's a kind of another way to think about it, consistent with the way that we've been describing it. Okay, any questions about that? Okay, so in question number 9, notice it's the same, the left side of the equation is the same. What is different here, kind of like you had on the quiz, is now the right side of the equation is different. And so because the left side is the same, right, we still have the same homogeneous solution. And so if we're trying to come up with a guess for this particular solution, when we've got a product of an exponential term and a trig function, then our initial guess would make sense to be something similar, namely a product of the exponential and the trig function. So what might be wrong with this guess so far?
You need to add a sign to get rid of the other cosine.
Yep, that's right. So these sines and cosines, they come in pairs. So I also would need this term over here. And now we want to consider whether or not there's resonance. So we can take a look at this piece over here and say, do I see something like this in the homogeneous solution? Well, I have an e to the 3t over here, but this doesn't have the cosine in it, whereas this one does. So these two things would have to be the same up to a multiple of a constant. And so if they're different by something that depends on t, then it's not, there's not going to be any resonance here. So we're done. We don't need to adjust this at all. That would be our a good initial guess here.
For the one above, when it's at squared e to the 3t, if we put like if we put a t cubed in it, would it still work out? It would just be harder math.
No, that if you put a t cubed in there, that would not work out unless you still have a t squared term in there. So if you put like at cubed plus bt squared times this would work, and you would actually just find that a is equal to 0. So if you would add like extra terms, it's not that bad. It just makes the algebra a little bit worse. But you don't want to leave out terms that you definitely need. So in this case, if you were to guess this, maybe it's not the best guess because we've got this extra term that's unnecessary, but this would work. We would, again, just find out that this is 0. But if you only tried this term over here, you would not work it out there.
Okay, thank you.
Yep. Okay. Any other questions? And what I was doing over here is, if you want to try and do it this other way, is you could look at this forcing function and say, what would the root of the characteristic equation need to be in order for me to get something like this? And that's where you can identify, well, if I have an e, well, if I have a trig function here, that means the root must have been complex. And so I have a 3 for the real part and a 2 for the imaginary part. This side of the equation had one repeated real root, so it's different from the complex root, and there's no resonance there. Okay, any questions?
Are we going to work through solving some of these? Like,
Yes, so step 1 is coming up with a good guess. You want to be careful about that, because if you have a bad guess, you can spend a whole lot of time getting nowhere. So yeah, definitely we're going to solve some of these right now. Yeah. So I will, we can come back to number 10 shortly. This one looks a little bit different than the others because we have a t squared, an e to the 3t, and a cosine of 2t. So we need to think about what do we do when we have a product of all of these things. And hopefully your intuition about what you might guess will be correct, but we'll see. But any last thoughts about these two, 8 or 9? Okay, then we will check out the next worksheet, which is worksheet 12. And if anybody needs this, I can send it into the chat. Or not, it's not letting me attach a file. Ah, here we go. Okay, so that will be loading in a sec. Okay, so yes, so now we want to talk about, we've talked about how we can get a homogeneous solution. We've talked about how we can find a particular solution. Now I want to talk about how we can use both of those things to find a general solution to a non-homogeneous differential equation. So we've been finding one solution, but not the most general one. So just to kind of take us through the full process, yeah, we can find the homogeneous solution by setting up the characteristic equation. And then if we have distinct real roots, we've been saying we get solutions like this for the homogeneous part, repeated roots. And here is what we would get for complex roots. And if we have a forcing function, which is non-zero over here, then for the particular solution, we would guess things that look like this. And just remember that when you have a sine or a cosine, then you should be guessing terms that have both the sine and the cosine in them. And then, as we've been talking, if you have resonance, then you need to multiply by t until that resonance goes away. Then you plug this in, solve for the undetermined coefficients, and now you've got your particular solution. So that's just a recap about how we found each of those types of solutions. Yeah, so let's kind of talk about how we can find the general solution. So we can prove this, and let me just say that this proof is pretty similar to the last question on your homework assignment that was due on Monday. So what we're going to say is YH, that's the solution to the homogeneous solution, to the homogeneous one. So if we had 0 over here, whatever this forcing function is, y of p is going to denote a particular solution associated to that. And so the claim here is that the general solution is going to be the sum of those two solutions. So what this tells me over here is that A, YH double prime plus B, YH prime plus C, Y sub H. If I plug that into the left side, if it's the homogeneous solution, then what should we get?
Zero.
Yeah, we'll get 0 for this. That's what it means to be a homogeneous solution. When we plug it into the left side, it gives us 0 on the right side. And then we also know, based on the fact that y of p is denoting the particular solution, that when I plug this into the left side of the differential equation, what should I get?
F of t.
Yep, because it is the particular solution for f of t. Good. And so now what we want to check is what happens when I try plugging this into the original differential equation over here. And what happens is, because derivatives of sums break up, we can take the derivative of a sum by taking the derivative of each thing separately and adding them together, that we're going to be able to break this up and collect terms in a nice way. So one way to show this is to plug it in. So I would get A times y double prime plus B times y prime plus C times y. And now let's just plug in what we defined y as, which was the sum of these two functions. Right, so now what happens is these derivatives can get filtered right through the sums. So I'll do that like so. And we're just using the fact that when you take the derivative of a sum, it's just the sum of the derivatives. So that's what we would get if we plugged in this solution. And then what do you think might be a good idea to do next?
Separate them so all of your homogeneous and non-homogeneous parts are together.
Yep, so we'll bring all of the h terms together. That would mean we would have A times this plus B times that plus C times that. And then we group all of the particular solutions together, this term, and this term. And just remember, this A would get distributed to both of those. So we have A yp double prime plus B yp prime plus C yp. And then from our assumption, we know this stuff in blue, because we assumed this was a homogeneous solution, right? That gives me 0. And the red stuff we just commented before over here would give me the forcing function, gives me f of t. And so when we add them together, what we can see is that when I plug this function into the differential equation, we do get the right side, which is f of t. We're getting the homogeneous stuff, which is 0, plus the forcing function. So it just gives us the forcing function. Okay, so any questions? So kind of the big takeaway here is that the general solution to these non-homogeneous differential equations right? We would take the sum of the homogeneous and the particular solution. So yeah, so here is a problem where let's go through the full details on this one. So not just come up with a guess, but find out what the coefficient needs to be and then come up with the most general solution for that.
Can I ask a question about what we just did though?
Yeah, of course.
The reasoning, why would we ever add 0 to anything? Is it for accounting so that we know what our homogeneous is so that we can tell if we have resonance? Is this just an allocation to see where we're at in the equation? What's the point of adding plus 0?
So I'm proving this, right? So
Right.
yeah, if you wanted to go straight to f of t, that's okay, but I think it's good to give a justification why this plus this gives me f of t, and it's because this thing gives me 0 and this thing gives me f of t.
Okay, thank
So
you.
I do think it's important to show that intermediate step because at this point we're using the fact that we were given this, and I think if we didn't know that this was a homogeneous solution, then this would not be 0 and we would not get f of t over here. Yeah. But we don't need to prove this every time we want to come up with the general solution. We can now use this result to generate the general solution. Okay, so I'd like you to at least now think about parts A and B. I want to make, or at least in part B, think about what the guess would be. I want to make sure that we've got reasonable guesses before I send you off into groups to talk with your classmates about this. So let's take a look at how part A would go. This is kind of the material that we started with, where we have second derivative minus first derivative minus 12x. So we're going to find the homogeneous solution. So we're just going to ignore that e to the 4t term. And then from this, we set up our characteristic equation. And then this one factors into r minus 4 and r plus 3. Oops. And so our general solution, since we have two distinct real roots, would be something like c1 e to the 4t plus c2 e to the minus 3t. So that kind of handles that piece of the puzzle. And then we've got f of t is e to the 4t. So based on that, what might be a good initial guess here?
So the first thing I would probably guess is AE to the 4t and then check for resonance.
Okay, and do we have resonance here?
Yes.
Yes, we do. That's right. So we just commented that this would be a homogeneous solution. So we have our initial guess is going to be a homogeneous solution. So plugging that into the differential equation would give me 0, not e to the 4t. So yeah, then we need to therefore multiply this by a power of t. And now does this have resonance? It does not, right? And so now we can compare this to this term, and it differs by not just the constant, but it differs by some expression of t. This one's not even close to this one, so we don't need to worry about this second term. So this would be a reasonable guess. And so what I'd like you to do with your classmates is to then take this guess, plug it into the differential equation, and figure out what A has to be. So solve for that undetermined coefficient, and then we can give our general solution. So keep in mind, our general solution should only have two undetermined constants, these general constants. And so we shouldn't leave A in our answer, but we should figure out what A has to be. So any questions? What to do? Okay, then I will split you up into breakout groups just to work out the algebra. So the question here is solve for A. So yeah, so it seems like a couple of groups were still finishing it up, and some of the groups got it, and the ones that wrapped it up, they all got the same answer, which is the correct answer, which is that A should be 1/7. So to see how that goes, we just need to be careful when we take the derivative of our guess. That should be an x, in the sense that we have a t there, so you use the product rule on that. So we would have the derivative here would be a e to the 4t plus 4at e to the 4t. We take the second derivative. And so these are what I'm getting for the derivatives. And then we plug it into the differential equation and group terms and try and figure out what A needs to be. So I would have, combining these two together, 8a e to the 4t plus 16a, 16, yeah, a t e to the 4t. And then we have the derivative was a e to the 4t plus 4at e to the 4t. And then we have minus 12x, which would be minus 12at e to the 4t. So that's what we would get plugging in our derivatives. And then you can observe that this cancels those two terms, right? So we have a positive 16at e to the 4t, and we have a negative 16at e to the 4t. So this is what always should happen if you've chosen the right guess. You should see that all of the terms that have that extra t in it should cancel out, because I don't have any of those in the forcing function. And now what's left over, grouping these terms together, is 8 minus 1, which gives us 7a e to the 4t, and that should equal the forcing function, which was just e to the 4t. So this tells me 7a should equal 1, which is the coefficient in front of the e to the 4t there. So that's where the 1/7 comes from. And so we have a homogeneous solution, which was c1e to the 4t plus c2e to the minus 3t. And now these are x's, sorry. And now we found a particular solution, which is 1/7 t e to the 4t. So we figured out what a is, so now we can substitute that value back in over here. So then altogether, the general solution would look like this, the sum of those two functions. Any questions? And so if you did have some initial conditions, you would just handle it the same way as before. Just, plug in the input, set the output equal to what's given, and then solve for C1 and C2.
Do we have to do that when we have the solution given to us? Or sorry, the particular solution, or can we just do that with the homogeneous solution?
You need to do that with the particular solution as well. Yeah, so if you had some initial conditions like x of 0 equals 5, x prime of 0 is 10, then you would plug 0 into this, for example, and this would tell you you get C1 plus E2. When I plug 0 in there, I happen to get 0 here, but that's not going to happen all of the time. So yeah, you do need to include that particular solution when you do both of these conditions. So when you find the derivative, you would want to take the derivative of that. Yeah. Okay, any other questions? Okay, so now I want to think about, well, what happens when we have a forcing function like the one that you can see down here in 4, where we have a sum of two different types of functions, right? Our forcing function is not just a trig function, and it's not just, we can consider this like a power function with the power being 0. So when we have a forcing function, which is like a sum of different components of forcing functions, then what we do is we find a particular solution for this, and we find a particular solution for this, and then we can add the two particular solutions together. So we do the similar thing that we did previously. We find the homogeneous, and then for each piece of the forcing function, we find a particular solution that works. And that's what question 3 is getting at. So I'll just leave this. I think this would be a good exercise for you to practice at home. It follows very similarly from question 1 that we did together. And I'll put up the solution if you want to check your work with it.
And Professor?
Yeah.
You mean when find the particular solution for each, we just act as if the other one isn't there? Like if we're trying to find the 85 sine 2t, we just act like 18's not there, find that particular, and then at the end, sum them?
That's right. Yeah.
Okay, thank you.
Yep, and we'll summarize that right now in question 4. Yeah. So what this looks like is, yes, we're going to find the homogeneous solution, x of h, by solving x double prime plus 10x prime plus 9x equals 0. And let me just say, we've done all of these problems in the previous worksheet. These would be in worksheet 9. We did some of this. In worksheet 11, we did some of it. So in worksheet 9, in worksheet 9, we did homogeneous solution. So we found this homogeneous solution. This characteristic equation has roots of -1 and -9. So that's where this homogeneous solution of C1 e to the -9t plus C2 e to the -t comes from. Yeah, and then what Kyle was describing was then we would want to solve each of these particular solutions separately. So I'm going to solve what is the particular solution associated to the 85 sine of 2t. And I'll just say on worksheet 11, we went through this and we actually solved for the undetermined coefficients in this particular guess. And that's what gave us, I'll call this particular solution number 1, which was -4 cosine 2t plus sine of 2t. And then we do the same for the forcing function of 18. This was the very first one that we took a look at. And this just had, since the forcing function was a constant, the particular solution was a constant. And so now the general solution would be the sum of those 3 pieces. So I take the homogeneous plus particular solution 1 plus particular solution 2. So that would be our general solution, be the sum of those three things all together. Okay, any questions? So the good news is we don't have to do anything new, right? We just kind of extend what we've been doing. Okay, so last sort of ones that I want to take a look at. So we talked about what happens when we take a sum of two different forcing functions, then we come up with each of the particular guesses separately, and then we sum them together. When we have a product, and maybe this is very similar to the one that we skipped for the moment on the previous worksheet. If we have something like this, where I have a product of power function t squared and an e to the 6 t. So for the t squared part, we talked about, well, we would guess something, the most general looking quadratic thing. And for this piece over here, we would guess, just to pick a different letter, some constant times e to the 6t. So when we have a product of these two, the good news is, if you're thinking, well, I'm just going to take a product of our guesses, and that's the right train of thought there. So my guess here would say, let me take a t squared plus bt plus c. I don't need that arbitrary constant d because it would just get absorbed into the other arbitrary constants. And so coming up with the guess is pretty similar. This one would be a bit challenging. It would be a little bit time consuming to actually try and plug it in, figure out what A, B, and C are. So then we see something that we might want to be a little bit careful about with this guess. What would be good to know in order to make sure we've got the right particular solution?
Check our check
Yes.
our exit page.
Yes. Yeah. And so, yeah, some people say homogeneous, some people say homogeneous. It's fine. Potato, potato. Yeah, so we want to find the homogeneous solution to see if there's resonance. And so the homogeneous solution here, the corresponding characteristic equation, just to do some scratch work, would be r squared minus 5r minus 6 is 0. So that has roots of 1 and minus 1. So the homogeneous solution would be C1 e to the 6t plus C2 e to the minus t. And what do you guys think? Do we have resonance here?
It almost looks like the polynomial could be a constant, but it has the variable inside of it.
Yeah, so some of the terms in the particular solution don't have resonance. Some of them do. So if, just for the sake of writing this out, if I were to distribute this through, right, there's no resonance with that in the homogeneous solution that I have in red. That's fine. If I had a repeated root, I might have resonance with that, but we don't because we have two distinct real roots. Okay, but the problem is with this last one. So this piece over here, which comes from this piece over here, has resonance with that piece. So we want to make sure that we don't have any resonance in any of our terms. And if we do, then we need to multiply by t. So we would want to adjust this solution by multiplying our initial guess, every single term in it, by a power of t. And now I wouldn't have any resonance in any of the remaining terms. And so that's why we put this t over here.
So your t is only multiplying the polynomial to try and cover up the c at the end. It doesn't get, never mind, I found it.
Yeah, so yeah, you could distribute all of that out together, yeah. But what's important here is now you would have a cubic term, a quadratic term, and a linear term, but no constant term. So that gets rid of the resonance. So any other questions about that? Okay. And to take this to the final extreme, if we have something like this, which is a product of a quadratic and an exponent and a trig function, then our guess is going to be a product of all of those things. So in this case, I'm going to guess the most general quadratic times e to the 6t times the sine of t, but then just remember, can you guys hear that? That's a cat that's like this big somehow making that much noise. Yeah, so when we have these trig functions, we need to include both the sine and the cosine in it. So that goes here too. I also want to include the cosine piece of this. And so for that, we could have different coefficients. So I use different letters for these undetermined coefficients. And here I would have e to the 6t times the cosine of t. And I should say that you would want to be careful and check for resonance here. And it's the same, since we have the same left side of the equation, the homogeneous solution here is the same as in the previous case. So that was a 9t, it was minus, sorry, it was 6 and minus 1. And if you check for resonance here, we're going to be okay because every term in this particular solution has either a sine of t or a cosine of t in it, whereas our homogeneous solution had no sines or cosines anywhere. So we don't need to adjust this by multiplying by t. Okay, any questions? Okay, so we've got 10 minutes to go. So let's give question number 7 a shot. And just so you guys know, we've got an exam, not next week, but the following week. And you will definitely see a question very similar to this on the exam. So on the exam, you'll definitely have to do some problems where you just tell me what the guess is and not have to spend all of the time solving for the coefficients, and there'll be somewhere I ask you to solve for them. So in this case, I'm not asking you to solve for the undetermined coefficients, but think about whether or not you can use this method and then what your guess might be. So I'll split us back up into the same breakout groups as last time, or maybe, I think they're still here, just to bounce some ideas off each other. So we'll take about 5 minutes in the groups, and then we'll wrap it up together. Let's consider these examples. And so if I'm trying to come up with a guess for a particular solution for all of these, what might be good to know?
What the homogeneous equation would be of the top.
Yeah, that's right. So we're always going to want to find the homogeneous solution here. And since we have the same left side of the equation for all of these, right, it's going to be the same. So we would have like r squared minus 8r plus 12 is equal to 0. And so from this, you should have found that the homogeneous solution, no, it's positive. Is this. Okay, and then we kind of come through our guesses. So let me just kind of ask a meta question here, which is for which of these options, A through F, if you've had a chance to go through them, are we going to have resonance? So am I going to have resonance in A? No, right? Anytime you see a sign and your homogeneous solution doesn't have any complex roots, not going to be resonance. So I'm just going to put in X to denote no resonance here. For the same sort of reason in B, we have no resonance. So although we have this e to the 6t, the fact that we have this sign over here means we're not going to have any resonance. Okay, tangent. I don't see how we're going to have resonance with that. What about D?
Yes.
Okay, we will have some resonance, that's right, because of this e to the 2t over here. So maybe we can take a look at that one in particular in a second. So that one does have resonance, and these other ones do not. So there's only one of these that has resonance. And the other thing I want to just clarify here is we haven't discussed the tangent. And in fact, this method won't work for tangent. We haven't discussed what happens when we have negative exponents, negative powers. And this method also doesn't work when we have negative powers. So this method of undetermined coefficients works if the forcing function is a polynomial, is a trig function, is a sine or a cosine, I should say, or is an exponential function. For other sorts of functions, this process doesn't work. And let me say, it doesn't mean you can't solve it. This means we just need to try another technique to do this, and that technique is called variation of parameters. So if you're curious about that process, it is in section 2.5. When I posted it, I slashed it out just to indicate that you don't have to read it. But if you're curious about it, certainly you're totally capable of solving these as well. Okay, so just the last thing before we end for today. So just to consider this case in D, since this is the only one that had resonance, right? My initial guess here would be something like a linear function times this exponential function. And the reason why we have resonance here is from this stuff over here. The b e to the 2t is exactly the same as this piece over here. So this one does have resonance, so therefore we need to multiply this by t. So I can write it like that. Maybe that looks like an x. So we need to multiply it by an extra power of t. Okay, so I will stop here. We'll do some more work on this on Monday, and we can take a look at some applications. We'll come back to the mass spring system and some other applications of this. And just so you have the picture for the next couple of classes on Wednesday of next week, we'll start looking at systems of differential equations, and that won't be on the first exam. And then in 2 weeks, when you do have your exam, on Monday, we'll just spend the whole class reviewing for the exam, and the exam will be on Wednesday, not this 2 weeks from today.
Will there be a homework due on the Monday, the Monday week of the test?
There will not be homework that will be collected. I might put up a homework assignment with some suggested problems and the solutions that you can check yourself, but I'd rather use my grading on the exams as opposed to the homework. So this way we won't have that much new stuff anyway. And this way we can just focus on grading your exams. Yeah.
And then the suggested homework, that'll act as like a review, hopefully, for the last few things.
I'm going to put up some review problems as well.
Cool.
Yeah.
Thank you.
Yep. Okay, so thanks everybody. We are out of time today, but if you have any questions, feel free to hang around. Otherwise, I've got office hours tomorrow, or have a nice weekend, and I will see you on Monday.